These are notes 2.4. We're going to talk about the correlation, the R, and we're going to calculate it, and we're going to talk about some properties of it and how outliers influence the correlation as well. Okay, so to calculate the correlation, it's kind of complicated. We're going to, on the homework, I'm going to ask you to do one of these just so you get the idea of how to do it. But first, we have to find the mean and the standard deviation of the explanatory, the x variable. And then we're going to calculate the z-score for each individual point. Okay, then we're going to do the same thing for the y. So we're going to find the mean and the standard deviation of the response variable, the y variable, and calculate its z-score. Okay, so that was this part and this part. So the z-score for the x, the z-score for the y, we're going to multiply those together, and we're going to find the sum of all the different points, and we're going to divide it by n minus 1. Okay, so we're going to start by looking at this data right here. Okay, so I'm going to put this into Desmos and find the mean and the standard deviation for each of the x's and the y's.
Here I have put the data in here for x is our foot length and y1 is our height. So if we want to find the mean and the standard deviation, I can go to functions, go to stats, and if I want to find the mean, so I can find the mean of x1, okay, it's 26. And to find the standard deviation of x1, go to functions, stats, standard deviation of x1 gives us 3.9. Okay, then I want to do the same thing for y. So I can just go back here and just type a y in there instead of the x. So for y1, our mean is 168, and our standard deviation of the y1 is 15.5. Okay, so that is how you find the mean and the standard deviation.
Okay, so we're looking at the foot length and their height of 6 different people there. I found on Desmos that the mean is this and standard deviation is this for the foot length, and the height has a mean and standard deviation there. Okay, so next thing I want to do is I want to find the z-score for the x. Okay, so for this one right here, the z-score for the x will be the 23 minus the 26 divided by the 3.9, we'll use 3.95. Okay, and that gives you a z-score of about negative 0.76. Okay, now for that same point, I want to find the z-score for the y. So my y here, my score was a 167 minus a mean of 168, and the standard deviation divided by is 15.54, which gives you a z-score of negative 0.06. Okay, so then we want to take these two numbers and multiply them together. So negative 0.76 times negative 0.06 gives us an answer of about 0.0456. Okay, then we want to do the same thing for all the other points. So for this point, my z for this x is going to be 32 minus 26 divided by 3.95. That gives me about 1.52. So that's farther away from the mean, right? And then the z for the y, for this one would be 188 minus our mean and our standard deviation. And it gives us about 1.96. And if I multiply the 1.29. If I multiply the 1.52 times the 1.29, I get about 1.9608. Okay, and you want to do the same thing for all these other ones. Okay, so 22 minus 26 over 3.95 gives you negative 1.01. Okay, this one here we have 150 minus the 168 divided by the 15.54 gives you about negative 1.16. And I multiply the negative 1.01 times the negative 1.16, and it gives me 1.1716. Okay, so I want you to pause the video, and I want you to calculate these other ones here, and then unpause it and see what our answers are here. Okay, so here are those worked out. You can check your answers: 0.51, 0.51, negative 0.76, negative 0.32, 1.09, negative 0.84. And when you multiply those together, negative 0.1632, 0.5559, 0.6384. Okay, so what we want to do now is we want to add all these together here. Okay, so if you add all these together, I'll pause it and add it together here for you. Okay, when you add those all together, you get about 4.2591. And our formula says we want to divide this by n minus 1. Okay, so since there are 1, 2, 3, 4, 5, 6, we're going to divide this by 6 minus 1, or 5. And we should get an answer of about 0.84. Okay, and if we go to Desmos, I'll go to Desmos here, we'll see if that is our R value there, how close we got. So
I'm back here on Desmos again, and I want to find the R value here. So I'm going to type in the equation, y1 tilde m x1 plus b. And you can see here my R value is 0.8415. So we had 0.84 we were good. Okay, so good job.
So I will ask you in your homework to calculate one of those with not very many points. Okay, the next topic we're going to talk about, second objective, is to talk about some properties of the correlation. And these are pretty important here to know. These will be on a test or quiz. So if you think about how we figured up our R value, we found the standard deviation of our x times the z-score of the x times the z-score of the y, and divided it by, we added them together, divide by n minus 1. Okay. Now, what do you think would happen if instead of height and foot length for this x and y, what if I switch those around? Would it make a difference? Okay, let's think about this formula. When I took this times this, what if those just switched and this was the x and that was the y, right? If they switched those around, would I still get the same thing? Okay, think back to, commutative property back in elementary school. Like 2 times 3 is the same as 3 times 2, right? It wouldn't matter how those are multiplied. So it also doesn't matter which is your explanatory and your response variable when you're figuring out R. Okay, so even if you switch the x and the y, R stays the same. One important point. Okay. Another important point is R is not measured in a unit. We wouldn't say that this is R is equal to, we found 0.84. It's not equal to 0.84 inches or 0.84 feet or anything like that. It's just a number, 0.84. Okay? So if we look at these right here, these points right here, okay, so our original was height and feet, right, and foot length, and they were both measured in centimeters. Now, what if we changed this and made it inches instead of centimeters? Okay, now looking at our formula here, a z-score is based upon where you are compared to everyone else. Okay, so is this point still a certain distance away, a z-score away, even if it's in inches? Okay, yes, it is. The z-score is still the same spot, same percentile, same everything compared to everyone else, whether it's in inches or in centimeters. Okay, so even if we change the units, okay, which will change the x and the y axes, right? Change these numbers. It won't change the R. The correlation is still going to be 0.84. Okay, and I think I already talked about this one. R has no units of measurement. It's not in inches or anything. It's just 0.84. Okay. So if we look at this problem here, okay, the 40-yard dash, how fast people can run, and the long jump distance. So the faster people can run, lower time, and the farther they're going to jump. Okay. So the correlation here is negative 0.838. Okay, so point A. What would happen to the correlation if it was plotted on the x, and the dash time is plotted on the y. So if we switch those two around, okay, what would happen to this r value? Now our graph would look a little different, but our r value would not change, stays the same. Okay, what would happen if the correlation, if long jump distance was measured in feet instead of inches? So if we just take this, put this feet instead of inches, what happens? Once again, the r will stay the same. Okay, r does not change. Okay, part C. Sabrina claims the correlation between long jump distance is negative 0.838 inches per second. Is this correct? No. Okay, once again, there's no measurement. Okay, so r is just this number, not inches per second. So we want to get rid of that one. Okay. Next, we're going to talk about how outliers affect the correlation.
That we did earlier. Now, let's say I put an outlier in here. Okay, so we look at this correlation, the 0.84, and let's say I put in here, let's see, the highest goes up to 28. So I'll go 30, so it's not too far out there. Okay, and let's go with 130, so it's really pretty low there. Okay, so as soon as I type that in there, what happened to the line? Okay, my r definitely decreased in it. Okay, it was 0.84 before, now it's at 0.27. Okay, and if we look at our data here, you can see this point right here had a drastic input on that. Okay, let's look at this as well. Let's say I change this value. Okay, so once again, it's back to the 0.84. Let's say it's fairly in the middle of all this. So I'm going to make it at 25. Then I'm going to make this value a really, really low number. So let's put it at 100. Okay, so did that make a huge impact? Okay, so it changed the line a little bit, and it definitely impacted our R value, so it's not nearly as tight. Okay, now let's see what the impact has on it. Okay, so here's our points again, right? Let's say I have it really far out here on the X variable. Okay, so let's say I'm out at like 50 and 100. Okay, look what happened to that line. It actually was a positive slope before, and now, based upon this point right here, it actually drew it down to be a negative slope. Okay, so it now has a negative slope to it, and then 0.66. So you can go to Desmos and play with this a little bit. What happens when it's an outlier in what direction? Here, let's see, let's make this 150. Okay, so if it's an outlier in the X direction versus the Y direction, play with it a little bit and see what happens to your line. We'll play with it a little bit more, but definitely makes it less correlated, right? Okay, so the outliers definitely bring down your R value. Okay.
Okay, here's another example of this. Okay, without those outliers there, you can see the correlation would be, I don't know, a little bit tighter. But with those outliers here, it is a lot more spread out, so that R is going to become closer to 0. Also, it could even possibly even make it a negative correlation. Okay, so outliers do have a big impact on the R value. Okay, so that is the idea of what we're talking about there today.